Hi folks, we're going to take a look at number 1 from the Unit 6 quiz. So here what they've given us is two functions which are defined as just a set of coordinates. Okay, so we're not given an equation, we're not given a graph. These are the only points that are in the functions f and g. Okay, so start with the first one, f minus g at 4. So the way in which we define these arithmetic combinations is they're just defined as the operation on the individual function. So in this case here, we take f at 4 and we subtract it by g at 4. Okay, so we look for f at 4 and we see that f at 4 is equal to 0, and then we subtract g at 4 and g at 4 is equal to 5. And so our final answer is negative 5. Okay, and it would work the same way with any of the others, addition, multiplication, or division. Now let's take a look at B. Here we have a composition, so this works a little differently. First, the input goes into the function nearest it. Okay, so the second one in my composition. Okay, so first I take g of 2. Then that output becomes the input to the second function, which is the one on the left. Okay, so this is how we calculate a composition. So first thing, again, we work from inside to out. So the first thing I have to calculate is g at 2. So g at 2 is equal to 3. And now it's this output that becomes the input to f. And if we look at f at 3, we get negative 1. Okay, in C, we're doing another composition, except it's the same function that's being used. However, let's make sure we're applying it correctly here. First, 2 goes into g. Okay, the one that's closest to it. Okay, and so g at 2 is equal to 3. Okay, and now it's this output that gets put into g a second time. Okay, and so here g at 3 is just equal to 0. Okay, let's move on to the next one, domain of f over g. So here f over g of x is defined as, similar to the one up in A, it's the quotient of the two individual y values. Okay, so in order for this to be defined, well, clearly x needs to be in the domain of each function, and we can't take anything that makes the denominator 0 because we'd get something that's undefined. Okay, so here if I look at the domain of f, what do I get? Now, if I'm asking you for the domain of one of these functions that's defined as a set of points, what I want to see is just a listing of x values. Okay, so you won't be putting in like an x as an element of R because we're not taking the values in between. We're only taking the exact x values that are part of this function. So in this case here, it's 0, 1, 2, 3, and 4. Okay, similarly for the domain of G, I'm only interested in those x values that are in this domain of G, which are just 1, 2, 3, 4, 5. Okay, now what I'm interested in is those x values that are in both domains. Okay, so I see here x is in not, 0 is not in both domains, so that one's going to go. 1, 2, 3, 4 is in both domains, but 5 is not. Okay, now the other thing I have to check for is, do any of these inputs to g give me an output of 0? Okay, and if we go back up to our function, we see that g at 1 is equal to 0, so we're going to cancel that. And we see that g at 3 is equal to 0, so we need to cancel that. So in the end, the only x values that satisfy the conditions are 2 and 4. Okay, so in other words, these are the x values that are in the domains of both and don't make the denominator equal to 0. So let's move on to this one here. So the domain of a composite function. Okay, so again, let me rewrite it as f at g of x. Okay, in other words, first I apply the function g, and then that output becomes the input to f. Okay, so the first thing we need is we need x to be in the domain of g. Okay, we'll write that out again. Okay, since g has to be applied first, so I can only take those x values which are in the domain of g. Now, in order to find the domain of the composite function, the outputs to these values must be in the domain of f. Okay, So if we're looking for F circle G, okay, we take each of these inputs one at a time. So let's take 1. Okay, 1, G at 1 is equal to 0, and 0 is in the domain of F. Okay, so that means my original input of 1, yep, that's going to be in my domain. Let's check 2. 2 becomes 3, and 3 is in the domain of F. So that means x equals 2 is also in my domain. Let's check 3. 3 becomes 0. 0 is in the domain of F, hence we take 3. Let's check 4. Okay, G at 4 is equal to 5, but 5 is not in the domain of F, so we're not going to take that value. Now let's check 5. G at 5 is equal to 1, and 1 is in the domain of F, and so x equals 5 is a valid input. And there's my final domain. So in this one here, I'm actually being asked to find this function. Okay. Now, if these were both given by equations, I'd expect an equation as an answer. Or if I was giving you these as graphs, I'd be expecting a graph as an answer. So since they're given as a set of ordered pairs, my final answer should be, again, a set of ordered pairs. So I'm not going to write out all of them, but essentially what we'd be doing is you take, again, those numbers that are in the domains of both functions. Okay, so what's in the domain of F plus G? Okay, well, we kind of already figured that out before. We don't need to eliminate those which give G at x equals 0, since I'm doing an addition. Okay, so the domain that's in both, remember, is 1, 2, 3, and 4. So my final answer should contain 4 ordered pairs. So let me calculate one of them. If I have F plus G at 1, that's equal to F at 1 plus G at 1. Okay, and F at 1 is equal to 5. Okay, and G at 1 is equal to 0. So my final answer would be 5. So that means that one of my points is going to be x equals 1, y equals 5. Okay, now I'm not going to write this out for each one. The rest I'll do in my head. So let's take an input of 2. Okay, so I have f at 2 is negative 4, g at 2 is 3. So negative 4 plus 3 is equal to negative 1. So that's my output value. Okay, input of 3. Okay, we have negative 1 plus 0 is negative 1. And my last point, when I take f at 4 is 0 and g at 4 is 5, 0 plus 5 is 5. So input of 4 gives me an output of 5. And this would be my final answer. Okay, that's it for these.